We got homework 14 on Saturday, and then homework 15 on Monday, and then exam number 5, which covers only chapters 13 through 15 on Tuesday. Obviously, a study day for that following 10th. That exam, excuse me, on the 8th, basically is another study day. So there's questions. I'm going to be here. We won't have any lecture unless we run into a snitch or problem. We have to continue with 15, but I don't think that will be the case. So basically, you got the 3rd, the 8th, and the 10th. I'll be here. You come in regular time, and or my 4:15 class, same scenario. You can come. You're welcome to come to that one too for questions and so forth. The density, I did move the extra credit density. I moved it to be due on the 16th because I got to get the grades in by the end of the week. So the 16th, so right the day after the final. Now, what that it entails is it's a file. It's in the section where the final exam is. So it would aid the final exam as far as points is concerned. I believe it's going to be, I got to check my notes, but I believe it's 10 points. But basically, it's a simulation. Open up the file, the digital file. You don't need to print it out because what you want to do is there is a link that you can, you click it and it sends you to the simulation site run by University of Colorado, and it deals with density. And then from there, just follow the instructions in the Word file that I sent. Now, basically, you're determining the density of a variety of different blocks, either a constant mass or a constant volume. The thing to remember, what you do is you grab that, when you grab that block, you immerse it into that liquid. That liquid will begin at a certain volume. And I tell you this now because sometimes that's not seen right away. So that there's a container with an X amount of volume to begin with. So you grab the cube and you immerse it into the liquid completely. So you got to hold it underwater if it's a floater. What that does is whatever volume you started off, obviously the volume goes up. Now, the volume of that cube is not the total volume that goes up. So if you start at 100 mils and you end up at 120, that cube did not displace 120 mils. That cube displays the difference between where the volume ended up, volume amount versus the volume where it started. Okay, and that is the volume you use for calculation of density. Keep track of your sig figs. Plug those numbers in back into the digital file, the Word document. Then once you're done, save it. There's a format there with your name and so forth. And then go back into the assignment, the extra credit assignment, and submit that document. Then I will get noted that it's been submitted and now graded. Okay. Now, sometimes what's happening, Flash, with some software that some simulation and other things require are not allowed to run. The Flash is slowly going out of business, but it's still available. If you're using Chrome and you click the link and it won't allow you, note up here on the left-hand side that where it gives you the address. If you can see where I pointed the mouse, let me highlight that. If for some reason you click the link and it doesn't allow you to run the simulation, I included information how to make sure you can get it to run. But if not, try this first. Go up to the far left. You'll see a icon of a lock. Okay. Click that. And here it might show up and say Flash not allowed or something. If in here, in my case, I do allow it, so it's already by default. But if you don't see anything about Flash immediately, and click the site settings, okay, which will send you to another site, another page, and look for Flash. You see Flash right here? Right now at this site, it is blocked, but you can easily unblock it. So you see flash right there? Okay, right now it is blocked. But if what you do, just hit the down arrow, allow it once, I believe the choices are. We'll click it, see what happens. Yeah, allow. And then do F5 on your computer. Now refresh the page, and then that simulation will work. Okay, so try that first and see if that works for you. Like I said, Flash is being slowly phased out, and all the simulations are being converted to HTML5 format. So eventually we won't need Flash at all. All right, any questions about that? And that is for the extra credit. So click the lock icon, go to site settings, look for Flash, allow it, refresh your page, and then run the simulation. Okay, any questions? All right.
Well, I did have one. I have a Google device, period. I have a Pixel book, and no matter how many times I tried to allow Flash, it still won't allow me to do it.
Did you go through I'm assuming you're using Chrome.
Yeah.
Yeah. Have you gone through this scenario I just showed?
Well, I've been having my fiance trying to help me out with it because he's a computer programmer, and he was still having
trouble. Give that a shot. Go to that little icon. Okay. So that, see, the icon is locked up. I mean, that means that certain things are being blocked. Okay. And click the icon. You see on my computer?
Yeah.
Okay, click that. A window drops down with some information. It may not have a flash option here, like I only have camera, microphone, and so forth. Go to site settings.
Okay. All right, I got it.
Got it? And then from there, go down to flash and then allow.
All right, thank you.
Yeah, because I know Chrome will support it for a little bit of a time period. And after that, Flash is going to be totally out the window.
All right, thank you.
Okay, sure, no problem. All right. Any other questions? No? Well, we're going to talk about coffee. Speaking of coffee, have a cup here. Basically, we're talking about solutions. Some of this stuff is pretty self-explanatory. You're familiar with it. You've seen it. You know, we come along and put names to it. Okay. But, all right. So what is a solution? A solution is basically a solute dissolved in a solvent. Okay. And the solute generally represents the chemical that is in the smaller amount, where the solvent obviously is whatever chemical you use that is in the larger amount. Now, we tend to think of just aqueous systems, and that's fine, but we can also have non-aqueous systems. We can even have solids that are solutions, so forth, by definition, okay? But the most common solvent is water. Okay, so obviously here we got a couple of containers of glasses of it looks like a Kool-Aid drink. Obviously you can see the concentration. In this case, it's a color solution that as we go from left to right, that just by the color itself gives us an indication as far as concentration is concerned. In fact, we use this technique in real life because we have instrumentation that can measure the concentration, the color intensity of light passing through. And we can actually use it to determine the concentration of unknowns, okay? So anyway, dilute solution to the left, very small solute, concentrated to the right, a lot of solute, okay? There is a limit as far as how much you can dissolve, solute you can dissolve in a solvent. Now, we have other examples of solutions. For example, a gas in a liquid, okay? Carbonated soda. anything carbon, any type of gas in solution, oxygen in water if you have a fish tank, you know, the oxygen is very important for the fish. Okay, so a gas in solution is a gas in a liquid is an example of a carbonated of a solution. You can have a liquid in liquid like a drink, you know, vodka and tonic, any type of mixture there. Okay, we got vodka in low concentration, hopefully, and tonic in high concentration. You can also have a solid in a liquid. Basically, you have taken sodium chloride, table salt, you dissolve it in water. Okay, so you have a salt water solution. You can have a gas in the gas, where air is a good example of a solution, where we have nitrogen, oxygen, high concentrations, and all kinds of other trace gases that are in our environment. Okay? Now, solid in the solid. A lot of people don't think of this as a solution, but it is. For example, steel. Steel is not pure iron. Steel is a combination of iron with some carbon, and that carbon is placed in the iron in certain mixtures to give you certain strength. A lot of the rings that we wear are not pure gold. Yes, they're gold, but they're not pure gold because pure gold in itself is very soft and doesn't lend itself very well to make jewelry because, you know, if you make a ring of pure gold, smack your hand, you can smash that metal. It's very soft. Okay, so the cardinal rule, back to polarity, polar material dissolves in polar solvents. Okay, like dissolves like. Polar solutes dissolve in polar solvents. Right? And the counter to that is nonpolar solutes dissolve in nonpolar solvents. Case in point, sodium chloride again. I put that in water, we know it dissolves. Take some sodium chloride in the morning and you put a little butter to fry up some eggs, throw some sodium chloride in the pan. That sodium chloride won't dissolve because it's ionic compound. And the butter is very nonpolar, okay? They won't dissolve in that butter. And we know that we also see that when there's oil spills, we got a big mess because nonpolar and polar do not mix very well. Okay, classic example right here with the oil mixture. Now, when we're dealing with liquids, okay, that mix with each other, we say that they are miscible in each other. So we got a liquid A, solute A, which is a liquid. We dissolve it in solvent B, which is a liquid. We call it miscible. Okay. When they don't, it's immiscible. Now, when we're dealing with solids, okay, if it's a solid that dissolves in the solution, it's soluble. And if it doesn't dissolve, it's just insoluble. So solid and liquid, we use the term soluble or insoluble. Liquid and liquid, we use the term miscible or immiscible. Okay. Now, the solubility rules here, again, we can't forget them, but we utilize them here. Now, not all solvents are water, as I stated earlier. It tends to be the most common solvent, but you can use a variety of different chemicals to constitute a solvent. And so here the question is asked, will these solutes dissolve in solvents? Okay, so on the top axis, we have HCl, hydrochloric acid, I2, which is iodine, PCl3, or trifluorine, trichloride phosphorus, okay, and CH4, otherwise known as methane. Those are the solutes. The solvents are on the left column. We have NH3, which is ammonia, and then we have C12H26, which could be anything, but we know hopefully by now that all we see is carbon and hydrogen. So we have this is a general formula for a hydrocarbon, okay, and Br2, which is a diatomic bromine. Okay, so what we got to do first is determine the polarity of each one. Because once we know the polarity, then we know if this is going to dissolve or not, if it's going to be soluble or insoluble. Okay, so NH3, ammonia. Does anyone remember? This is ammonia right here. Okay. If you didn't know whether this compound was polar, what could you do to determine its polarity?
The Lewis dot structure.
Exactly. You do the Lewis dot structure, and you'll find out that we have the nitrogen, the central atom, and 3 hydrogens bonded to the central atom. And then you end up with a lone pair on that nitrogen. That lone pair takes up a lot of space compared to the others. And as I mentioned before, every time you see a lone pair on a central atom, you automatically think polar. So we have a polar species. Ammonia is very polar. Okay. What about C12H26? What do we know about the carbon-hydrogen bonds with respect to polarity?
That because of the relationship between C and H, it's nonpolar.
Exactly. Carbon-hydrogen bonds always, like the diatomic atoms or molecules, are nonpolar. And since we have here nothing but carbon and hydrogen, that formula C12H26 does not tell you anything about the structure. All you can deduce from that is that you have nothing but carbon and hydrogen. It's a hydrocarbon. Being a hydrocarbon has nothing but carbon hydrogen nonpolar bonds, therefore we have a nonpolar solvent. Okay. And then we have Br2, which is diatomic, and we know that diatomic compounds are nonpolar. All diatomics are nonpolar. Okay. And so what we have up here is ammonia being polar. We come to that conclusion. Okay. The hydrocarbon being nonpolar. Bromine, which is diatomic, is nonpolar. Okay. So to answer the questions here, we have to find the polarity of all the chemicals involved. HCl. What can we say about HCl with respect to polarity? You have a 50-50 chance here, either polar or nonpolar. Okay. What do we know about the hydrogen chloride bond? Is that a polar bond or a nonpolar bond?
It's nonpolar.
Try again. Okay, to have a nonpolar bond, okay, is to remember this. To have a nonpolar bond, okay, a nonpolar bond will always would be a bond between two elements that are the same, okay, all the time. And that includes the carbon-hydrogen bond because the electronegativity of those two are the same, okay? So anytime you see a bond between two elements that are the same, nonpolar. The moment you replace one of those A's with a B, which is telling you, I got another compound there, something else, some other element. This is always will be polar, the bond. I'm talking about the bond itself, not about the bond, not about the overall molecule, okay? I'll review that here in a second. All right, so with that being said, HCl is represented by AB because we got a hydrogen and we got the chloride, two different elements. So automatically it's a polar bond. Now the direction the polarity goes to, and that means, remember the arrow that we would draw? Thank you. Okay. That is dependent on the electronegativity of the two elements involved. Okay. And how do we determine electronegativity? You remember what benchmark, what reference point we use to determine the electronegativity as far as comparing two different elements? What do we use?
You use fluorine as your benchmark.
Exactly. Fluorine is the most electronegative element out there. Okay. And so if we're going to compare the electronegativity of two different elements other than fluorine, because if fluorine's there, then it's by default, it's the most electronegative, nothing beats it. But if we're comparing two elements that are not fluorine, we look at their position on the periodic table and find out which, and look and determine which one's closer to fluorine. Here we have hydrogen, here we have chloride, okay? Chloride is much closer to fluorine than hydrogen. Hydrogen's in the far group 1, way near the far left of the periodic table. And so the electronegativity is pulled toward the chloride. And hence, I wrote the arrow in the direction of the hydrogen to the chloride, okay? Which results in a partial negative on the chloride because it's pulling the electrons toward itself. Now, the next one, I2. I2 is represented up there, what I wrote on the top left, as AA. These are two elements exactly alike. That bond between them is equally pulled. They're shared equally. The electrons are being shared equally because the electronegativity are the same. Unlike HCl, in that bond, that single bond between the hydrogen and the chloride, the electronegativity is not the same. And therefore, that bond sharing is more toward the chloride. It is unequal bond sharing. And when you have unequal bond sharing, you have a polar bond. So I2, iodine, is nonpolar, okay? And then we have PCl3, trichlorophosphorus, okay? Much like, very similar to NH3, if we do the Lewis dot structures, guess what? We end up with a polar, we have lone pair on that central phosphorus. So we got an automatic polar molecule there, okay? Now, if that was PCl4, okay, just for example, if that was PCl4 with 4 chlorides around that central phosphorus, all that phosphorus and the chloride, there are 4 polar bonds, but they get canceled out being in the tetrahedral position. Therefore, the net result would be that it would be a nonpolar species, okay? And so if your polar bond is canceled out by another polar bond in a molecule, then you end up with a nonpolar species, okay? I think that's where sometimes it's difficult to remember. If your molecule has all nonpolar bonds, like the next example, CH4, methane, carbon, hydrogen, as stated, is a nonpolar bond. If it has all nonpolar bonds, automatically it's a nonpolar molecule, okay? If your compound has, where'd it go? If your compound has polar bonds, normally they're polar, the molecule is, unless the polar bonds get canceled out, okay? That's the thing to remember about this. Okay, so we have HCl, which is polar. Let me write this out. We determine polar. Okay. We have iodine, which is nonpolar. We have PCl3, which is polar. And then why would CH4 be nonpolar again?
Because it's a hydrocarbon.
It's a hydrocarbon, and they have nothing but nonpolar bonds. Okay. All right. All right, let me ask you this question now. With respect to IMF interactions, okay, looking at the solute just with IMF interactions, what IMF forces or intermolecular forces, which one would HCl have? Anybody want to take a guess? Remember how many intermolecular forces we have? We got 3. Actually got 4, but the 4th one dealt with ion polar, which dealt with ionic compounds and water. And here we got no water, we got no ions. So we're dealing with London dispersion forces, dipole, or hydrogen bridging force.
Would it be a dipole?
The HCl would have dipole. There is a dipole bond, okay, in HCl. And so it's either going to be either dipole or hydrogen bridging. It can't be hydrogen bridging because the only examples of hydrogen bridging are those hydrogens bonded to, remember, not on file, nitrogen, oxygen, or fluorine. This is not the case. The hydrogen is bonded to the chlorides. So the IMF force here would be dipole, okay? So this would be dipole for hydrochloric acid. What about iodine? What force would be involved with that?
London dispersion.
Got it, because it is nonpolar. All nonpolar compounds would have London dispersion forces, okay? Then we have apolar, PCl3. What forces do we have here? Well, it can't be London, right? Because it's polar. We just determined it's polar. And so what I'm left with is either hydrogen bridging or dipole. Can it be hydrogen bridging? No. Why? Because there's no hydrogen there. It's phosphorus and chloride, right? So what is left? Dipole, okay? And then methane. It's nonpolar. What does that tell you automatically, the force that's involved there?
London dispersion.
London dispersion. Okay. But it's all entwined here, you know. And so if I had to determine the one with the lowest, which ones, okay, which 2 would have the lowest boiling point of the solutes? I got 4 boiling points: HCl, iodine, PCl3, and CH4. I got 4 boiling points. That's the temperature in which they start to boil. So based on their forces, which 2 would have the lowest boiling point? But to answer that is ask yourself, of those forces, remember which is the weakest. The order of strength, the strongest force was the hydrogen bridging force. Next came the dipole, and the weakest was the London forces, dispersion force. Okay, so with that in mind, of those 4 solutes, which would have the lowest boiling point?
Either the iodide or the methane, right?
Yeah, and that's why I said the lowest 2. Because they would be the ones with the weakest force, which is the London dispersion forces. Okay. All right. So as far as solutes, the forces involved here would be the dipole for ammonia. And for the nonpolars, what do we got? London dispersion forces. Okay. So the solvents of here, the ones with the lowest boiling point would be the hydrocarbon and the bromine. All right. So enough of that. It's kind of refresh your memory on the London forces because it all comes back. This is, this type of question not only can ask about solubility and so forth, it's tied into the forces and polarity and the bonds and the Lewis dot structures and so forth. Okay. All right. So to answer the question here, which will these solutes dissolve in the solvents? But to answer that question, we got to remember like dissolves like. Okay. Polar dissolves polar. Nonpolar dissolves nonpolar. Okay. Good example, again, makeup. I sometimes it's my understanding to get rid of some of that makeup, some of that hurricane proof makeup, you got to use some oil-based material. Correct me if I'm wrong. Soap and water may work for certain types of makeup, but those that require an oil-based cleanser are very non-polar. And you want them to be non-polar because if they're out in the rain and the makeup runs, then you have you have makeup that has polar properties because the water is polar and it's dissolving your makeup. If you're in a hurricane and your makeup still looks good, has not running, then you have a very non-polar makeup, non-polar based makeup. Okay. So we got ammonia and hydrochloric acid. Is it going to dissolve? Let me clear the drawings. Okay. Ammonia and hydrochloric acid. The answer is yes. Okay. Why? Because both of them are polar. All right. All right. What about ammonia and iodine? Would they dissolve?
No.
Again, because like dissolves like, and iodine is nonpolar and will not dissolve in a polar solvent. The next one would be yes, because in both cases, they're both polar. Next one would be no, because we're dealing with a nonpolar and a polar. Okay. Now we're dealing with the hydrocarbon and hydrochloric acid. It will not dissolve because we got a nonpolar versus a polar. Yes, it will. Iodine will dissolve in the hydrocarbon because of polarity. Both of them are nonpolar. No for the PCl3 because we got polar versus nonpolar. Yes for the methane, obviously, because they're both two nonpolars. Okay. And no for the bromine and the hydrochloric acid because we got a nonpolar solvent and a polar solute. Yes for iodine and bromine. No for PCl3 and bromine because of polarity, polar versus nonpolar. And yes for the last one. Okay. So given a table like this, be able to answer, first you got to answer the question or to determine who's polar, who's nonpolar. Okay. All right. With respect to miscible, immiscible, soluble, insoluble, we have a polar liquid, polar solvent, then we use the term miscible. With the nonpolar solvent, it is immiscible. Okay. Nonpolar liquid, polar solvent, immiscible, obviously because of polarity. Okay. And miscible for a nonpolar liquid and a nonpolar solvent. Polar solid in polar solvent, soluble, because we're dealing with a solid and a solvent. Insoluble, dealing because again, we got a polar solid and a nonpolar solvent. Nonpolar for a nonpolar solid and a polar solvent, soluble for a nonpolar solid and a nonpolar solvent. Ionic compound, polar solvent, it depends on solubility rules. Okay, that's the only way you can answer those. In that case, it would be either soluble or insoluble. But keep in mind with the solubility rules, even though it is insoluble, there's a small amount still in solution. It is a weak electrolyte. And the last one, ionic compound and nonpolar solvent, would be insoluble. Classic example, table salt and say vegetable oil. All right. Well, the dissolving, not much to say about the dissolving process. We talked about this in previous slides. Here we have water, which is extremely polar. It has two dipoles. It has a partial negative side, which is solvating the positive ions here in sodium. The chlorides would be on the outside with the protons of water, and they'll be solvating the chloride ions. Okay. All right. So concentration. Okay, we have two types of concentration. When we talk about concentration, we have what's called the mass percent, which is a weight over weight percentage. Okay. Now, we have something else called molarity, which was introduced to you back when we were dealing with pH. Molarity is the ratio of your moles divided by the volume of solvent that you utilize. Remember the moles. Okay, you have X grams of a compound. You need the molar mass of that compound. You divide by the molar mass to give you the moles, because the molar mass has the units of grams per mole. All right, so calculating the number of moles, dividing it by the volume utilized gives you the concentration of molarity. Okay, now the mass percent. It's defined as the mass of solute divided by the mass of solution. And the solution incorporates the mass of the solvent and the mass of the solute. Okay. And we tend to forget that, but you got to include, we're talking about the mass of the solution. That means what material, the weight of the solvent, but also the weight of the material that we're dissolving in solvent. For example, it says calculate the mass percent for 15 grams of potassium nitrate being dissolved in 135 grams of water. Now, keep in mind, you're simply asking for the mass percent. There's no need here for the moles, okay? We're just simply talking about the weight. Okay, so you don't need to calculate the moles here. You're given the mass of the solvent, which weighs the water, which is 135 grams, took 15 grams of solution of potassium nitrate. And so you take that 15 divided by the sum of the solution times 100. That's a 10% solution. Okay. All right. There's other, we're going to do just mass percent, but you also have volume percent, mass volume percent out there. But we're going to just stick with mass percent. Okay. Now, occasionally, you may need to calculate how much water you need. For example, they're asking you here, how many grams of water are needed to make 5% saline solution with 10 grams of salt? Okay. And so I need to set that up because I'm given 10 grams of my salt, but I don't know the weight of the water. So I define that as X. Okay. And then I add my 5% times 100, because that's how I calculate the mass percent. So I'm trying to solve for X here. Now it looks like a very complicated algebraic equation. It really isn't. We're going to break it down here. Okay. Now there's a variety of ways to solve for X. This is just one way. And I tend to keep it simple system here. Okay, so that's our setup. I know I need 10 grams. I need to calculate what X is, and that is the amount of water that I need to use to make a 5% saline solution. All right, So the first thing I do here is I went ahead and multiply. I'm gonna move my 10 plus x to the left side. You see what they did? They multiplied by the quantity 10 plus x on both sides of the equation, which moves my 10 plus x to the left and cancels the 10 plus x on the right side. Okay? So it simplifies it a little better. Now at this point, you can go any multiple ways. You won't be wrong. But here in theirs, what they did was went ahead and multiplied the 10 times 100, gives you 1,000. Okay. Then what they did is they took that 5 on the left-hand side of the equation and divided through on both sides to move the 5 over to the right. So the 5 cancels. So I end up with 1,000 divided by 5. So I got 10 plus x is equal to 200. Okay, so because that's 1,000 divided by 5 is 200. And now I have 10 plus x equals 200. I just simply solve for x. I move the 10 over from the left to the right. So I'm going to subtract negative 10 on both sides to give me 190 grams, or 1.90 times 10 to the second grams. And so to make a 5% solution, I need 10 grams of the salt and 190 grams of water to make a 5% solution. Okay. And what do? We go back and check it. Take that x, plug it back into the equation, and do the math, and you should end up with 5.00 equals 5.00, which means x is correct. That's just checking your work. Okay. I moved it over to scientific notation. Why is it presented in scientific notation and not as 190 grams?
And that has to do with significant figures, right?
That's correct, because you have 3 sig figs here that you need your answer to be in. And so 190 only represents 2 sig figs. All right. Now molarity, and that is a ratio of moles of solute divided by the liters of solution. And one thing to remember, sometimes you might be given units of milliliters and need to convert that to liters. And remember that in 1 liter, there are 1,000 milliliters, 1,000. Okay, so here they're asking to calculate the molarity of 9.96 grams of potassium bromide. If 9.99 grams of potassium bromide is dissolved in water to make 2.5 liters of solution. Okay, well, like I said earlier, I need the molar mass. Well, before I need the molar mass, I need to make sure I write the formula correctly for potassium bromide. Okay, so here we go. We're writing formulas. Apologies, our neighbors going crazy out there. All right, so potassium. So I always recommended, I'm taking the words and writing the formula. So write everything as ions first. So what is the charge of, what is the symbol for potassium? Let me ask you that.
Okay.
Okay. Now, what is the charge for the potassium ion?
It's a +1.
+1. And why is it +1?
Because it's in the first column?
Yep, it's in group 1. It's got 1 valence electron, and it's a +1 because it's group 1 and it's a metal. Being a metal, it's going to lose an electron, and it's going to lose that 1 valence electron. Okay, so I end up with a +1. Okay, what is the symbol for bromide?
Br.
Br. Okay, and what is its charge?
-1.
Okay, and why is it -1? You're correct, but why is it -1?
Because it's in column 7.
Column 7, and anything else?
Well, it's next to the noble gases, and the noble gases are 0.
Yeah, okay, just like I stated, why potassium lost an electron, because it was a metal. What is bromine? A non-metal.
Yeah.
And what do nonmetals do? They gain electrons. And being in group 7, they got 7 valence electrons, so they're not going to lose 7. They're going to pick up 1 to get the octet 8. Okay, and so now those are my ions. Now I can put them together to write the formula. It's a simple 1-to-1. So the symbol would be simply KBr. Okay, now I can go find the atomic mass, molar mass, I should say, for KBr by determining the atomic weights of all of potassium and bromide, and actually end up with 119 grams. Okay, and so the molar mass is 119 grams per mole. I write it with moles in the numerator. Why? Because I want my grams to cancel, my grams of potassium bromide to cancel, leaving me with moles. So 9.99 grams divided by 119 gives me 0.08395. Don't truncate it yet until you're done with the calculations, because you can see eventually we're going to have 3 sig figs in the numerator and 3 sig figs in the denominators. Our answer should be with 3 sig figs. So take the number of moles and divide that by 2.50. The molarity of 9.99 grams of potassium bromide in 2.5 liters of solution is 0.0336 moles per liter. Okay. Now there's a lot of practice in the worksheets, a lot of examples. You may want to go through and practice them. If you have problems with them, bring them to Thursday or next Monday, and we can work through it. Okay, we'll do one more. Here, we want calculate M, the molarity, if 5.0 grams of sodium phosphate is dissolved in water to make 255 milliliters of solution. Okay, well, first things first, we need to write the formula of potassium phosphate. Excuse me, in this case, sodium phosphate. Okay, so we know sodium is Na, and ionic form of sodium is Na plus. We know that because it's in group 1. Just like potassium, it would lose that 1 valence electron. Okay. What about phosphate? What bit of information do you have that will help you determine the structure of phosphate?
Well, it's a polyatomic ion.
Polyatomic. So you can use a periodic table to determine what that formula is, right? So it should be what? PO4. Anybody know what the charge is?
-3.
So PO4 -3. All right. That's the phosphate ion. So now I got to put them together to write the formula. You can see that I'm going to need 3 sodiums. So that 3 becomes the subscript for sodium. So I end up with Na3PO4. Once I have the formula, now I can determine the molar mass, because I got 3 sodium, 1 phosphorus, and 4 oxygens. Look up the atomic weights of each one, and to sum them all up, we should end up with 163.94 grams per mole for sodium phosphate. Okay, so take 5, divide that by the molar mass. That gives me that 0.030, etc. moles. Again, we don't want to truncate it just yet until we're all done, because eventually we're using 2 sig figs for the 5.0 and 3 sig figs for the 255. So our answer should end up with 2 sig figs. We have 255 milliliters. We need to convert that to liters, okay, because molarity is moles per liter. And so we know that in 1 liter, there are 1,000 milliliters. Again, there's your conversion factor there, keeping track of your units. I cannot overemphasize using the system to keep track of your units, to make sure that things cancel out properly. You got it set up properly. And so that represents 0.255 liters. Now, if you know that you can just move the decimal point over 3 directions, then, by all means, go for it, okay? But if you're not comfortable and you still need a conversion factor, continue using the conversion factor until such time you can move the decimal point to get me to liters. And so now I do the math. I end up with, if I take 5 grams of sodium phosphate and I dissolve it in 255 milliliters of solution, the concentration, the molarity of that solution will be 0.12 moles per liter. Okay. All right. And congratulations. You have suffered through 15 chapters of chemistry. So don't forget whatever assignments we talked about, those coming up. There is a practice final exam on the website. Okay. I will be here Thursday. I will be here next Monday. And that's about it, really. So practice, do your homework and get ready. So it really has been a pleasure. We're trying to set up an evaluation system for you guys to do. I haven't been able to do that just yet, but I'll notify everybody when that comes to play, when I get that uploaded, because I really would appreciate any positive, not even negative, any feedback. This is totally new to all of us as far as doing this online thing. It's been a challenge, not only I know for you guys, but over here too. So anyway, any other questions, comments, concerns?